Okay, we're live. So welcome everybody. This is going to be a workshop, short 3-hour workshop for the data intensive biology training program out of UC Davis. And today we're going to be talking about regular expressions. So what are regular expressions? Regular expressions are patterns to match text. Okay, so this is very similar to find and replace in a Word document. So if you're interested in finding some sort of word like, I don't know, behavior in a large document, you can say find in Word, type in behavior, and it will highlight all the instances of that word behavior. So we're going to be essentially learning how to do that in Python. That's the goal today. So there's many times that you would perhaps want to do this. So for example, when you're working with text from a book, for example, or a manuscript. Other times you might want to do this in biology is when you're working with DNA sequence data. So maybe you want to look for transcription factor binding sites, for example, or where a restriction enzyme might cut. So we're going to go through some examples of that today. So regular expressions can be used in Python, but I don't want you to think of this as just a Python-only tool. This tool is implemented in many, many different programming languages. So you can use it in R, you can use it in Perl, you could use it at the command line using tools like grep or sed or awk. And the syntax that we'll be learning for regular expressions is very similar as we go along between the different languages. So how we're going to structure the workshop today is we're going to spend roughly the first half just focusing on regular expression syntax. And that's because it's a bit cryptic looking. And it's a bit cryptic looking because you're trying to match text with text. And so there's a lot of different special characters that will let us match patterns in text, but they might actually be part of the text itself. So there's a few, it can be a little bit tricky. So because of that, what I've done is put together a little regular expression cheat sheet for you. So if you go to the Etherpad and click on line 7, that link, you'll be taken to a markdown document that will have a bunch of the syntax that we'll be using. So I'll just click on it myself here. So these are some of the important syntax that we'll be using and a little description to the right for what each of them does. And then once we move into Python, I have a little cheat sheet here about what the different functions we'll be using in Python do. So you can refer back to this as you need to throughout the workshop. Going back to the Etherpad now, the other things that we have important links for, so we're going to be, as I said, we're just going to focus on regular expressions for the first half, and we'll be using a little web tool that will let us put in the text we want to search, and then has a little box for us to build our regular expression to match that text. And so we can just focus on learning that. Once we've mastered that, we're going to move into Python. So to do that, we don't need to download this yet, but we'll get to the point where there's some data that I'll need you to download. It'll be DNA sequence data. And then the last two links that are important on line 5 and line 6 are the notes for this lesson. So if you fall behind for any of these, and sometimes I might want to refer to a figure, this is where these are going to live. For those of you not familiar with an Etherpad, this is a public note-taking pad, so you can add text or notes in here. I'll ask you to do that at the very bottom here. I don't know what this call SMS Skype stuff is, so I'll just delete it. So yeah, you can add, we'll have some status of how people in the different sites are dealing with the challenge questions down here, and then feel free to add any notes in here that you might want to share with your colleagues, or you might want to look at later. Scrolling up, we have some input text that we'll be using, so I'll direct you to what you need to copy and paste when. So the first thing that we're going to do is we're going to go to the web app link. So this is on line 4. So if we can all click on line 4 on the Etherpad to go to Regexr. So this is the tool that we're going to be using. So when you go to this website, by default, there's a bunch of example text in there that we're not actually going to be using. So let's delete that first. So first thing we'll do is we're going to delete everything in the text section and everything in the expression section. Great. So how this web tool works is that we're going to put some text in the text section, and then we are going to build a regular expression in here that will help us find the text that we're looking, the subtext that we're looking for. We're also going to add another flag to this. So if you can go over to the right-hand side and click on flags, we want to do multi-line matching as well. That's just a special option for this tool. So we had global clicked and multi-line clicked. Okay, so the first thing, I'm going to direct you back to the Etherpad. And we're going to go to line 14, and we're going to copy the text from line 14 to 19. Please copy it and don't cut it, because if you cut it, it will disappear from the Etherpad. So copy this text and put it into the text box for the Regex tool. Okay, so we've got our text in there. Now we can start to build regular expressions to match this text. So one thing that we often want to do in biology when we're working with sequence data, if you're planning some sort of cloning, for example, you might want to look for restriction enzyme or binding sites. So let's work with that. So I've got an example table of restriction enzyme binding sites in the notes. So let's again go back to the Etherpad and click on line 6 to go to the notes. So here, if we scroll down, I have a table here of restriction enzyme binding sites. And so, for example, we can search through this sequence and look for sites that bind to EcoR1. The way we do this would be to simply type in the EcoR1 recognition sequence. So let's go ahead and try that. So we're going to type in GAATTC. And we can see that in this text that we're searching, or this sequence that we're searching, there are 2 instances of this restriction enzyme binding site. Pretty simple. Okay, what if we wanted to look for not only EcoR1, but we also wanted to look for BAMH1, because we're doing a double digest. We want to know where it's going to cut if we put both of these enzymes into the restriction site. So what we can do is we can use, we'll bring into our first bit of syntax in regular expression, is an OR. So the OR is the straight up and down character on the right-hand side of your keyboard. And then we can type in the BAMH1 site. And now we can see that a third restriction site shows up. So we're not only matching the EcoR1 site, but we're also matching the BAMH1 site. Now, when you're using regular expressions, whitespace is extremely important. Whitespace counts as a character. So if we put a space, for example, here, we no longer have the matching of the BAMH1 site. We lose that. Similarly, if we put a space at the end, we lose that because it's looking for then BAMH1 followed by a white space. That lost. They're back? Okay.
Yeah, we see you again, so it's okay.
Okay, great. And we're broadcasting again? Yeah?
Yeah, we're still broadcasting. Just,
Okay.
you know, a little.
No problem. Okay, so I'm going to keep going. What did you guys follow up until?
Until the white spaces part.
Perfect. Okay, you didn't really lose
Right
anything.
after that.
That's great. Okay, so let's head back to the notes and take a look at the other restriction enzymes that we might want to match. So for example, what if we want to look at the EcoR2 restriction enzyme site? If we take a look at the recognition sequence for this restriction enzyme, we see that it binds CCWGG. Wait a minute, what's W? So oftentimes in sequences, there's some special notation when something can be either one of 2 or one of 4 different nucleotides. So if you look in the notes here, a W means it can be an A or a T, and an N means that it can be either an A, T, C, or G. But if we try and write this directly into our regular expression, that's not exactly going to work because there's actually no W in the text. So let's take a look at how we can solve that problem. So if we go back here and we try and work with the EcoR2 site, we type in, I just got to go back, yes, that's what I'm looking at, CCWGG. So as I said, it doesn't work. So another special symbol that we could put in is the period, or the dot. This will match any character. So you can see now that we're getting CCAGG as well as CCTGG. So this is pretty good, but when you're doing regular expressions, you should always not only test for things that match, you should also think about testing for things that don't match. Because what if you also got some data in that looked like this? If you use the period, that's going to match, and that doesn't make any sense for a DNA sequence, for example. So we don't want to match that. So another thing we can do is be more specific. So we could use we could provide a set of options to the regular expression, and we put these things inside of square brackets. So the options that we can provide would be A or T. Okay? So it's going to match CC, A or T, not A and T, A or T, and then GG. Okay, so what I'm going to stop for now is we're going to hit our first challenge question. So what I want you all to try, so if we go to the Etherpad and you go to line 50, I want you to create a pattern with this Regex tool using to match the Boom H1 cutting site. And Boom H1 cuts C, T, G, C, and then 4 other nucleotides. So I want you to, your match should highlight 8 characters. And N can be A, T, C, or G. Getting some weird spamming in the Etherpad. It's back at the bottom? Oh, I don't know what's going on. So Davis and Ontario, let us know when you've solved the challenge question. And here at SFU, when you've solved the challenge question, put up a yellow sticky. So I'm just going to put the challenge question back at the top again. So we're working on challenge question 1. It's a fake one. Yeah, I think it's a fake. I think it's a fake restriction enzyme site. So yeah, don't Google it. Okay, they're done. Perfect. We're done here at SFU 2. Hopefully, Anne, your site is done as well. So let's take up the answer. So we're looking for the Boone H1 restriction enzyme site. So somebody in SFU, can you suggest the answer to me? What did someone try?
CT, GC, and then 4 consecutive brackets with AT, CG.
Great. So CT, GC, and then do this. Do the set 4 times.
Yeah.
Great. Awesome. That is definitely a correct solution. Copy and paste these. So that would find our Boom H1 fake restriction enzyme site. So that's great. This looks a bit long, though, right? We think that, especially if we had, what if we had, 10 ends afterwards? What we can do is we can start to use quantifiers, is the next topic we're going to go across, to make these the syntax a little bit more concise. So let's move away from the Boone H1 example, and let's just talk about a simpler example. We'll just talk about finding repeats of T's in the sequence. So to find one T, we just type T. If we want to find match T 1 or more times, so we're looking for any single occurrence of T's or runs of T's, we would use the plus sign afterwards. And so we get T exists as a single or up to infinity repeats of T. But in reality, we don't really consider a single T a repeat, right? So what if we want 2 or more T's? Then we can use this curly braces notations. So if we just put a single 2 inside here, and we say we want exactly runs of 2 T's. If we want 4, we would do that. But we can also say a span. We could say 2 to 4. That will give us 2, 3, and 4. Or we can say 2, comma, and then just leave that empty. And when we do that, that means 2 T's as a minimum and up to as many as infinity T's in the sequence. Great. So what if we wanted to look for dinucleotide repeats? That's something else we might want to do. So TA, replications of TA. So you might think that you could do this. But then if we look at what it's matching, it's not exactly what we're looking for, right? So what we're getting here is T and then a run of A's, where what we want is TA, TA, TA. So what we have to do is use another special character, the brackets, to do some grouping. So if we put round brackets around here, this will apply the quantifier to the whole group and not just the last character. Great. So again, I'll just repeat that. So if we do just TA on its own, the quantifier here is only applying to the character preceding the quantifier, unless we put the grouping notation, and then it will apply to whatever is included in that group. Okay. So that's great. So what if we're interested then in a sequence that goes TA repeats, and then we want TA repeats that end with one, that could end in G, a repeat of G, or nothing. But we don't want TA repeats that end in C or A. So what we could do there is we can add a single G on the end. That's giving us a TA repeat that ends in G. But if we want to say that we also want the TA repeats that don't end in G or that end in multiple Gs, we can add another quantifier, the asterisk. So this means match 0 or many times. So there can be a G, there could not be a G, or there could be multiple Gs. And if we wanted to be a little bit more specific and just say 1 G or no Gs, we could use the question mark. So that means match 0 or 1 times. So I'm throwing a lot of notation at you here. That's why I've given you the cheat sheet. And so trying to think, is there anything else? There's one other example I'm going to show you, and then we're going to move on to a new challenge question to get you to try and implement these things. So the challenge question we're going to be using is going to be working with phone numbers, not DNA sequence. The same types of things we've been learning apply. But I want to show you how to match a range of a set of numbers. So I've showed you how to match, 1 or 2 nucleotides. But what if you have the numbers 0 to 9 or 100, and you want to match all of them? Obviously, you don't want to write them out 1, 2, 3, 4, 5, 6, and so on. So let's erase everything in the text and everything in the expression window. And then we're going to head back to the Etherpad. And on the Etherpad, we're going to move to line 22. And we're going to highlight line 22 to 25 and copy that. And we're going to paste this as our example text that we're going to search through. And so what we want to find here in this example text is I want to find all of the numbers. So we know that, for example, if we wanted to match the number 5, we would put the number 5 there. And we can see that there's a lot of different numbers. So we've learned about sets. So we know that if we put numbers inside the sets, it will match things. So if we go 0, 1, 2, 3, 4, 5, 6, the numbers start to highlight, but this seems really redundant. So a quicker way to do this is we can give a range. We can say match everything from 0 to 9 inside that set. Okay, so I think I provided you now with enough tools to try the next challenge question. So the next challenge question, if we go back to the Etherpad, is on line 58. So I want you to copy line 60. Oh, so before we move forward, Titus has a question. In DNA example, how do we handle end-of-line issues? Is there an easy way? So before we get to the challenge question, let's step back and address that. So I'm going to recopy in the DNA sequence and talk about this a little bit. Okay, so when we're dealing with the DNA sequence, for example, what if we're trying to match AGGG? So we see that it matches AGGG here as well as here. But if you take a look at the top, the first line, we can see AGG. And if we go to the next line, there's a G here as well. And for a real DNA sequence, there's no line breaks in the DNA, right? This, like, it should word wrap and go all the way around. When we move into Python, the way that we're going to be importing the sequence, we're going to be using a tool that will remove all of the line breaks from the file that stores your DNA sequence. That's not happening here with this tool. I'll try something here. We can try an escape character. That works. Perfect. So at the end of a line, there are hidden characters you can't see that denote a line break. And a line break character is \n. So if in this tool we want to, or if you're using some other tool that doesn't work well with, that doesn't automatically strip the line breaks, you can use this. You could use this in your sequence. We can say AGGN and match as well as AGG. Or we could do something a little bit more creative. Perhaps put this a little bit more creative could be, or useful maybe would be, we put the G as well as the line break inside of the set. That's not giving us a perfect example because we're not getting multiple. We want 3 Gs. So we can put 3 in here, 3 or 4. That will give us a solution of how to match the line breaks. So here we have A. We're matching Gs and line breaks 3 to 4 times. Although we only want AGG, we might have a line break, so that would make it 4 characters. So that's how in this tool or another tool that's not going to strip those line breaks would work with the DNA sequences. Does anyone in this room or any of the other room had the questions? Yeah, Titus says, seems like the lesson is not to use regexr to search DNA sequences. Okay, so I think that's good to give us to talk about the line breaks. So let's go ahead and try now the challenge question. So we're going to move down to, I'm going to have to, oh, okay.
Every time I highlight the thing, it breaks.
Okay.
I apologize for that.
That's fine, no problem. So what I'm going to get you to do is copy it from the notes instead of the Etherpad if you're having that issue. So there's a challenge question here in the notes. You'll have most of it, so you can copy that. I'm going to recopy this back into the Etherpad. Okay. So, so we're going to copy this whole thing, both the valid and the invalid phone numbers, into the Etherpad. And we're going to, from the Etherpad, sorry, into the regexr. And what I want you to do is to try and come up with a regular expression that is going to match the valid phone numbers, but not the invalid phone numbers. So again, if Davis in Ontario can let us know at the bottom of the Etherpad how you're doing, that would be great. And I'm going to mute us here for a second. So I'm going to give just a couple more minutes here to work on it, and then we'll take up the answer.
Yeah, I can't. I don't think it's going to recommend time.
You can't just go 1, 0, 1.
Complete all of mine.
So this. Oh, that's what you're. 1 or no?
Yeah.
Isn't that 0 or 1? Wait. Yeah. A lot of leaving spaces there. So you get all that white space again. Because you have blank or hyphen, right? Yeah.
All right. Since Davis is done, I'm going to ask Davis to paste an answer, or anyone at Davis that has a working answer, paste it in the Etherpad under line 70. And as well as anyone at the other sites that has a working answer, if you have a different one from the ones at Davis, paste it in the Etherpad under line 70. Great. So anyone here at SFU, I see a couple yellow stickies. Paste your answer. Same with Ontario if you got one. And let's take a look at Davis's example with the Regex tool. So it seems to work. It matches the valid phone numbers and not the invalid phone numbers. So it's using a couple things that we haven't seen yet. So let's look at these. So this one is a special character that will say you have to start the match at the beginning of the line. Okay? So don't start matching anywhere else, but only at the beginning of the line. This other special character here at the end means match the end of the line. Okay? So this regex has to be bounded by the beginning and the end of the line. The first one can happen 0 or 1 times. So you could use this notation. You could probably also replace that with the question mark, so we can give that a shot and see if that works. That still works. So you could have a question mark or the 0 or 1. Then we have either a space or a dash, maybe. So that's what the question mark. It happens, or it can happen. It doesn't have to happen. Then we need to have 3 digits. Then maybe it could have a dot in it. Then it has to have, oh, maybe it could have any character. That's what the dot is. Then we have to have another 3 digits. Then it can have any character, and then we have 4 digits. So let's take another look at the Etherpad to see if there's any other examples of solutions. So let's take a look at this one that's quite similar. This one. And we've got a white space issue, and so this one also seems to work. So you don't need necessarily for this solution the bounding characters where you have tag the beginning and the end of the line. Couple different things in this one is they used a question mark for the 1, and they used some more groupings here to to grab the possibilities of the spaces or the white space. Yeah, so I think that's pretty great. So there's a couple different examples of how we could solve that problem. Okay, so what we're going to move on to next is we're going to look at another case where we want to match some emails. So if everyone could go to the Etherpad and copy the text from line 29 to 44 into the Regex tool. And again, if you're having trouble with the Etherpads, this is also in the notes. So if you scroll down in the notes, you'll see this text as well. So again, we're copying the text from line 29 to 44 in the Etherpad into the Regex tool. Okay, so what we're going to try and do here is to match these valid emails and not the invalid emails down here. So let's take a look at them first. So the valid emails have basically typical word-like characters in them. They can have letters, they can have numbers, they can have underdashes or spaces or dots. They have to have an @ symbol. And then after the @ symbol, you have a domain name, dot, and then like a .ca or a .uk. When we look at the invalid emails, we can see that they contain spaces, they might contain apostrophes, and then we've got some funky things going on in the domain. So we don't want to match domains that start with a dash. They can contain a dash, but they can't start with it, and ones that don't have a dot in them. So let's give this a shot. So we need to learn a few new tools to efficiently match these regular expressions. So we're going to start off again using this anchor to the beginning of the line that we had seen in Titus's example from the last challenge question. So this means match the beginning of the line. And then we're going to just focus on matching. Right now we're just going to work on matching the text before the @ symbol for the email addresses, right? And then we'll build up from there. So if we want to match these texts up until the @ symbol, we can see that, well, first, for example, for the first one, we're interested in letters. So we can go A, B, C, D, E, F, G through the entire alphabet, but again, that's really long. So you can imagine from what you've seen with the letters that we can do something similar. So we could say, for example, A to Z to match all of the lowercase characters, and we want to match them one or more times. Okay? So we're anchoring to the beginning, matching characters A to Z, lowercase, one or more times. Now, what about, why aren't we matching the second email? This is because it has a capital case B. So we have to be explicit about that as well. So we can say A to Z in capital letters. Now, there's nothing that we have to put between these two different spans, the lowercase a and the uppercase A to Z. There's no comma or anything. You just stack them together. Now, there's a few other things that we are not matching. So the under, we can add the under dash as an option that we're going to match. And then there's also some numbers in there that we need to match. So we have to match 0 to 9. And so let's just pause there at a second. There is something special about all of the things that we've just put in there. There's another more concise way in regular expressions to represent all of these options because they're very common things that we see in word-like text or file names, for example. And so we can use the, instead of writing all of this out, we can use the \W and it will do the same thing. So that's going to match upper and lowercase characters, digits, as well as under dashes. So again, that should be in your cheat sheet. Okay, so we're getting there. So we've got many of the things. So just one other thing to know about the \W, you don't need this set notation. It will work without the set notation. But because we want to also include this dot as well as the dash, we are going to use the set notation because we're going to include that as well. We're going to say it matches any word-like character as well as the dot and the dash. Now, you've seen the dot before, and I told you that it matches any character. But here, because it's found within the square brackets, it's exactly matching a period. It's not matching any character. So that period outside of set notation will match any character. Inside the set notation, it matches specifically that dot. Okay, so we have matched the first part of the valid emails. You can see that we're matching some of the invalid emails, but we still have work to do. We're going to try and now match the rest of the emails, and that's where I'm going to hand it over to you. But before we do that, we're going to take a coffee break. I think we're doing 15 minutes. Is that right, Davis? Yeah, okay, great. So we're going to break now, come back here at 10:30, and we will move right into the challenge question then. And I'm just going to mute our microphone until coffee break's over. Okay, so we're back from coffee break. Just want to check in that Ontario and Davis is back. Let us know in the chat of the Etherpad, please. Awesome, everyone's here. Great. So what we're going to move on to next is we were just starting to come up with a regular expression that was going to match the valid emails in this list and not the invalid emails. And so we've developed a regular expression that matches the first part. So I'm now going to leave you with the challenge question to come up with a regular expression to match the entire, to finish it to match the entire email. So again, Ontario and Davis, let us know when you're done working on this. At SFU, give me a yellow sticky when you've solved it, and then we'll take it up. Maybe I'll check it. Can you ask?
I don't know, actually, sorry.
I know, right?
Okay, I'm just going to give us one more minute here at SFU because they, in Ontario and Davis, they had worked on it. They were keen. They worked on it during coffee break.
So similar to oh, because you're Bruno Grande? Oh, so the reason that one got thrown off, yeah, I probably did the same thing. So you know how after your @ sign you do another like /W type thing, or A to Z? has to include the dash dot, otherwise this dash needs to drop, right? So after your @ sign, it has to be simulated.
All right. So what I'm going to ask people to do now is if under the challenge question number 4, so on line 79 on the Etherpad, if people from Davis, from Ontario, and SFU could put in the solution if they were able to get a solution that worked, that highlighted the valid but not the invalid emails. So let's take a look at this solution from Ontario. So this is a solution from Ontario. We see that it matches the valid emails and it doesn't match the invalid emails, so that's fantastic. So let's take a walk through and see what they did. So they started off with the caret to anchor it to the beginning of the line. And then they used a set very similar to or exactly what we had done previously. So we said that it could match any word-like character as well as dashes and periods. Those were acceptable. And then it explicitly, there had to absolutely be an @ sign. And then there was a, then we had a group. And the group had to have a word character, start with a word character, then it could have a dash, and that could happen 1 or more times. Then there had to be a period, and then we had a lowercase letters 1 or more times. So this is an acceptable solution for the test cases that we gave here. And then that's great that we have quite a few more in the Etherpad. So after the workshop, you can go feel free to test out a few different ones. Oh, we've got a question as to why this one does not work. Let's take a look. So this one doesn't work. I'm not, to be honest, I'm not exactly sure why this one doesn't work. I think it might have something to do with this. But, oh, this is a negated set. Okay, we're not going to get into that, but I'll let people explore that afterwards. I think it'll just take too much time. So at this point, what we're going to move on to is we've done, I think, a good job of getting introduced to regular expressions using this tool. And I mentioned this at the beginning of the workshop, but I'll mention it again, that regular expressions, again, are not specific to this web tool and not specific to Python. Many different languages implement regular expressions. So you can use them in Python, you can use them in R, you could use them in Perl, for example. And you also will encounter them with many of the command line tools that you use. So if you regularly use grep, awk, or sed, regular expressions are also used in those tools. And so this knowing regular expressions is actually quite a very useful skill set to have, no matter what you're doing and what tools you're using.
You used to work in Microsoft Word.
Oh, they used to work in Microsoft Word, but they don't anymore?
I think in 2013 they didn't really work very well unless maybe you had to install a plugin. But
Okay.
like, you can search for acronyms if you're like writing your document.
Okay, very cool. Yeah, I know they also work in certain plain text editors as well. So I use Text Wrangler, and you can use that as well. Okay, so what we're going to move on to now is we've finished with the web app, and we're going to move on to using this tool, using these tools now in Python. So the first thing that we're going to need to do is get the data, the sequence data that we're going to work with. So if we can all go to the top of the Etherpad, excuse me, and click on line 5, this should download a zipped folder to your computer. If you could unzip it and put that on the desktop of your computer, that would be fantastic. And give me a yellow sticky when you've got that done, and if Davis and Ontario could let me know when they have that done as well.
just call it a folder?
Yeah, I want you to unzip the folder. It's called data, and have the data directory on your desktop. Excuse me.
Yeah, I just policy. That's my desktop. I already have. That's what the error sound is.
Okay, so it looks like most people have got it done at SFU, and everyone at Davis and Ontario is done. So I just want to show you what's in this data directory. So in here we have 3 different FASTA files, or FASTA files, and they contain sequence data. Oops, I'm just going to, no, we're good. Just thought I heard a noise that I need to pay attention to. Okay, and so we're going to be searching these sequence files for regular expressions for specific sequences that we want to find. So just to give you a little, just going to show you what these sequences, what FASTA looks like if you're unfamiliar. So I'll just open it up in a text editor. So what we've got here are 6 different sequences. These are very short sequences. Some of the other files have long sequences in them. And the format for these sequences is that they always start with a greater than sign, followed by some text, which is usually the sequence name. It can have some other optional information. And then you have the DNA sequence followed on another line. Okay, so the difference is that there's a line break between the sequence name and the DNA sequence. So we're going to be bringing these into Python. We're going to be using the screed package to do this, so hopefully you have this installed ahead of time. If not, the TAs in your room should be able to help you with that. And then once we bring it into Python, we're going to be querying it again for the regular expression that we're interested in. So before we dig in, I want to set up the problem that we're going to try and solve with regular expressions, with this, working with this sequence data. So I'm going to go to the second set of the notes. So that's in the Etherpad on line 7. And I'm going to show you this figure here. Hopefully that is big enough. So many of you have probably heard about CRISPR. Even if you're not a biologist, in the news, it's in the popular news. It's a really fantastic new gene editing tool that lots of people are using. Now, CRISPR did not evolve to be a gene editing tool. It evolved as a bacterial immune system. And so that's the aspect of CRISPR that we're going to be playing with today. So how this bacterial immune system works, very, very briefly, I'm not an expert on this, is that your bacterial genome can incorporate pieces of viral DNA of viruses that attack it. Okay? And so then it gives it some sort of almost memory of that virus. And so the next time it encounters that same virus, it can recognize that sequence and chop up that DNA. Very similar to how RNAi might work. And how that is, those pieces of viral DNA are encoded into the CRISPR genome is in a very specific way. So in this diagram here, what we have is this looks like a linear genome. Bacterial genomes are generally circular. And so these these different rectangles represent different pieces of viral DNA from different species of virus this bacteria might have encountered. And then these black diamonds represent repeats in the bacterial genome that flank the virus DNA. So when you're analyzing this, if you're studying this field, it would be fairly easy to look at the genomes and see these repeats of bacterial DNA, but you might not know in the bacterial population you're looking at what viruses are potentially affecting those bacteria. So one thing you might want to do is search for those, use a regular expression to search for those repeats, to then pull out those spacer DNAs, so then you could figure out what viruses are attacking it via a blast search, for example. Does that make sense? Thumbs up, thumbs down? Yeah, okay. So we're going to have to load in a couple pieces of sequence DNA to do this. So we're going to load in a bacterial genome. And then we're going to load in that other FASTA file that I showed you, and that is the small repeat sequences. And then we can query the bacterial genome with those repeat sequences. Okay? So let's jump in and do that. Okay, so we are going to start by opening up a IPython notebook. So to do that, let's first open up a terminal on your Mac or Linux, or Git Bash on your PC. And we're going to first navigate into the data directory we just downloaded and put on the desktop. So we're going to go cd desktop/data. Hit enter. And when you type ls, you should see those three FASTA files that we put there. So give me a yellow sticky if that happens and you see what you expect to see. Give me a red if you don't. And Davis in Ontario, let me know when you're all with us. We just need one more minute here at SFU. Okay, so most of us are there. So the next thing that we want to do now is to open a new IPython notebook. So to do that, we type IPython space notebook and hit enter. So when you open your IPython notebook, you should see the three data files. And we're going to start a new notebook. So on the right-hand side of the browser, you're going to click New, and then Python 3. Okay, so again, here at SFU, give me a yellow sticky when you see this new notebook open like this, and you see a cell that you can type in. And Davis in Ontario, let me know that all your notebooks open okay. Okay, so everyone's looking pretty good. If anyone falls behind, again, the notes that we're going to be working through are on line 7 of the Etherpad, so you should be able to catch up with the code. Okay, so the first thing that we're going to do is just rename the notebook. So I'm just going to call this Regex tutorial. And then the next thing we're going to do is we're going to import the library that we need to use to import these FASTA file DNA sequence files. So we're going to import libraries, and we're going to import screed. So again, if you haven't used the notebook before, when you see a number on the left-hand side of the cell, that means that it executed all right and things are looking good. I'm just going to add quite a few more cells to my notebook, and I'm going to toggle my header and my so it's a little bit easier to see. Enter full screen. All right. Perfect. Okay. So the next thing we're going to do is we're going to, like I said, we're not going to do it. This workshop isn't about how to get your sequence data into Python. So we're just going to copy the code that I've pre-baked baked for you ahead of time. It's all commented, so you can go through it afterwards if you're interested. So if we head to the Etherpad, I'm going to have to. Head to the Etherpad, and then again back to the notes, the one on line 7. Close this. Great. Just doing some housekeeping here. Okay, so if we scroll down to the second block of code here, I want you to copy this and paste it into your IPython notebook. So this is going to be loading the genome of the bacterial genome sequence. So we run that code, and file is not found. Oh, I made a mistake. We're not inside data. We're directly, there's a typo in there. So you have to remove data. So this is what your file name should look like. There should be no data ahead of it. And once you run that cell, what you should see is we have opened the file, and we've created 2 variables. The first one, genome seq name, is grabbing the basically the information after the greater than sign in the FASTA file. And the second variable, genome sequence, is grabbing the bacterial sequence. And we've just printed them here. And for the bacterial sequence, because it's very, very long, we've only printed out the first 100 characters. Does that make sense? Everyone's with me? Okay. So now we're going to go ahead and do the same thing, and we're going to bring in the sequences for the repeats that we're going to use to search the genome with. So we'll head back to the notes, and we're going to copy in the third block of text. Into here, and we're going to run this code. And so what we've basically done the same thing here is that we've gone through and grabbed the sequence name and the sequence for each of the sequences in that FASTA file. But since there's multiple ones, we put them in a list. And we had a list of the sequence names, and we had a list of the sequences, and then we've zipped them together to make a dictionary, so that we can then say, give me the sequence for this sequence name. Okay? And again, the file is not found because the code, I didn't have data. So you don't need data in front of the data files. So give me a yellow sticky here in SFU once you've got the data loaded. And let us know in Davis and Ontario that everybody has the data loaded, and then we'll move forward. Okay, so let's quit. Let's just close this and just try to open it. Okay, so go back to your git bash. Yeah. And let's just quit. Okay, so, oh, I think it's because it, yeah, so let's just totally ignore this project. Or, you know, you're in the right place, right? Yeah, so let's type IPython notebook. Space notebook. Okay, now let's try and do it. I think it just, the connection got lost. Yeah, so you're good. Again, Davis in Ontario, let us know when everyone at your site has an open notebook with the data loaded. Yeah. Okay. Do you have a launcher? Can you go here? Can you just type it in? Okay. And did you install it?
I think it might be.
Okay, I mean, it will work. Are you going to use Python? Okay, so if you're used to writing scripts and such,
I'm
you
just
can
trying to
start writing a
understand,
script.
like, I guess, like, cities. I'm just trying to understand, like the data corresponding to where it actually loads, like sequence name and sequences. Sure.
They're good? Okay, so we can move forward. Awesome. So, okay, so I'm just going to toggle my computer screen so it's a little bit easier to see. Okay, perfect. So, I've said that we've got this, basically this dictionary now where we can access the CRISPR repeats by their sequence name. So let's just take a look at how to do this. So let's select a sequence from the dictionary. So the dictionary's name is CRISPR repeats. And if we want to grab the first item in the first sequence name from the FASTA file, which ended in _1, we'd type NC 011761 _1. And when we do that, we should have a sequence output for us. So this is how we can access the sequences by their sequence name from this dictionary. And again, just so we can see how we can access the genome sequence, we're going to type genome _sequence. And again, we're not going to print the whole thing out because it's a bit big, but we can grab the first 100 characters, say, and print them out to screen. So these are the two things that we're going to need to be accessing right now. So just want to make that's clear. I'll just put a comment here. Select first 100 characters of the genome sequence. Okay. So let's start to look at how we can use regular expressions in Python. So to use regular expressions in Python, we're going to take advantage of another library. So we're going to use the RE library. So we have to import that. So let's import regular expression library. And so it's just simply import RE. So there's a couple functions that we're going to be using in the regular expression library. We're going to start off with the re.search function. In that cheat sheet that I gave you at the very beginning of the workshop, I have a list of about 4 or 5 of the functions that we'll be commonly using, and a little bit of explanation about what they're for, again, because it's a lot of information all at once. So, say for example, before we dig into solving our problem, let's just look at the syntax of using regular expressions in Python. Say we wanted to look for the first ATG, the first possible methionine sequence in this bacterial genome. We would do it as so. So we'll make a variable that's going to capture that. So we're going to call it first ATG. And that is going to be equal to re.search. And then we give re.search 2 things. We give it a pattern, and then we give it a query sequence. That's how this is going to work. Okay, pattern and then query sequence. Very easy thing to trip up on is swapping those two when you're starting to learn this. So just remember the pattern comes first. So if we're looking for ATG, our pattern is going to be ATG. And we actually want that ATG, okay? So we're going to put that inside brackets. That's our capture group that we're interested in grabbing from the sequence. And then our query sequence, we're not actually going to type out the whole genome sequence here. We're going to pass in the name of the variable that contains the whole genome sequence. So we'll type in genome sequence. So what happens is that if this finds a match in the genome sequence, then we're going to get a match type object back. And if it doesn't find a match, it's going to give us nothing back. Okay? So let's give this a try and see what we get. So it runs, but again, we don't know if it was successful. So we can say type, and then first ATG, and we can see that we get a match object back. So it matched something. So how can we actually grab what it matched? So match objects have, there's a group method that you can use to access the things that it matches. And you can have, I'll show you later, but we can have multiple capture groups, so we can capture more than one thing at a time. And you get multiple groupings for each capture object. So we only have one, so we're only able to grab one match. Okay. So if we want to grab that, we would say first ATG.group, and then we would ask for the first item, and that would give us ATG back. So that's what it found, the ATG in the sequence that we were looking for. And which ATG did it grab? It grabs the first one. So it's basically going to start at the beginning of the sequence and read through and grab just the first ATG. You might want to find multiples, maybe, and we'll get to that. So there's a different function to use if you want to do multiple searching. But the search is just going to give you back the first one. Okay, so I'm still not kind of convinced that that worked, right? It's just, how do I know it just didn't give me back exactly, this doesn't, is this actually regular expressions? It's just giving me back exactly what I typed in. So let's try a simple regular expression. Let's look for the first run of t's. Okay, so 2 or more t's. So let's call this, or we'll do a TA repeat, sorry. First TA repeat. And we'll use the same thing. So re.search, round brackets, and we give in our pattern. So our pattern this time is going to be TA, and then we're going to say 2 or more. And then we're going to, again, feed it the genome sequence. Then we will ask for the first TA repeat back. I don't know how long it's going to be. Might be just one TA repeat, or it might be multiple. And then let's take a look at what we get. Oh, and I didn't do grouping. So this is TAA repeats. So we're looking for T and then a run of A afterwards. That was my example. So this is the first occurrence of that. Does that make sense? Okay. So let's take a look at what happens now when we don't get a match. What happens after that? So I'm just going to add a few more cells. So let's go non-match is going to be equal to, so we're going to, again, use re.search. In our pattern this time, I'm explicitly making it something I don't expect to find. So DNA, genome sequence should be A, T, C, or G. Shouldn't have amino acid codes in it, right? Like Q, R, and S. We shouldn't find that. So let's put that there and then pass along the genome sequence again. And then let's look at the type of the non-match. And when we run that, we see that we get a none type back. And if we were to ask for the group of this object, we would get an error, okay? So, I mean, let's do that just so we know what that looks like in case we encounter that later. So non-match.group 1, and we get an error. It's telling us that the none type object has no attribute group. Okay, so everything good here. All right, I'm just going to check in on the Etherpad and see if there's any questions or if everything's good at Davis and Ontario. Okay, everything looks good there. Okay, so let's head back into, yep, still good, great. Head back into the notebook. So now let's look at matching or searching for the CRISPR repeat. First CRISPR repeat. So how will we do this? So what we're going to do is we're going to make a variable that's going to hold that called first repeat. And then we're going to use the RE search function again. And this time, our pattern is going to be a variable, CRISPR repeat. But if we type CRISPR, sorry, it's an item from the CRISPR repeats, right? We want to find this item. This is what we're looking for. If I explicitly search for this in the genome sequence, it's not going to work, right? It's also has to be like that. That's not going to work because it's going to explicitly look for capital C, then R, then I, S, P, R, etc. So we want to grab what's inside of that variable. So we can take advantage of string concatenation in Python. So I'm just going to show you an example below before we go ahead. So if we want to get the value of CRISPR repeats as a string, we've already seen this. We just type in the name of what we're accessing. But we want to put those brackets around it for the regular expression search. So to do that, we can put the beginning bracket inside quotes, and then use simple string concatenation with a plus symbol in Python. And then we do plus, quotes, and then the end bracket. And so now when we run this, this looks like what we would want to feed into our regular expression to make it work. Does that make sense? Okay. So essentially we need to put this inside the pattern up here. Copy it. So it looks a little cryptic, but it's actually quite nice compared to how some other languages might deal with this. So let's run the search, and now let's look for the first matching CRISPR repeat. Let's print the first matching CRISPR repeat. So again, we would grab our match item, first repeat, .group, and we only have one grouping, so we're going to do that, and if we print it, we get the sequence back. Okay. In addition to finding the sequence, I mean, we're not using a fancy regular expression here, and that's fine. I just want, I purposely made this somewhat simple so that we can focus now on the Python syntax of using regular expressions. And so something else that we might want to know about this sequence is not only that it's there, but also where is it. So from this match object, we can also get the position in the sequence of where it is. So that can be very useful. So we can get that by going first, repeat, .span. And we get the position of the first nucleotide in the sequence and the position of the last nucleotide matching in the sequence. So again, this could be very useful depending on what your application is downstream. Okay, so any questions in this room? Any questions in Davis or Ontario? Everything's looking good. Okay, great. So, when you're doing these regular expressions, sometimes it's more readable for your code as, oh, did you have a question?
Yes.
Yeah, sorry, okay, question.
So those numbers include that like C to the opposite C?
I think so.
Okay.
I think
so.
so.
I get confused if it's like one pass or like.
Yeah, to be honest, I can't remember.
Okay.
So, but we could play around with that later. Yeah, it's also tricky. It's always tricky in Python because it starts counting from 0, right?
Yeah. So
Yeah.
I don't. Okay.
Yeah. Okay. So what we're going to talk about now is compiling the pattern ahead of time. So this is a little bit cumbersome to read. Depending on how complicated your regular expression is, it could be a little bit even more cumbersome. The other thing too is that for memory usage, compiling the pattern or interpreting the pattern is more heavily memory usage than is actually searching for it. So if you're going to be using the same pattern over and over again, you might want to use a function to compile it first, and then you get an object back from that, and then you use that for your search. So we'll just show an example of how to do this ahead of time. So we will compile a pattern ahead of time for speed and readability. Okay. So first we'll specify the pattern and compile. So we're going to call this NC011761 100-1 pattern is going to be equal to RE, again it's using the regular expression library, RE compile, and all we give it ahead of time is this pattern. So we can just copy this pattern into the compile. Then what we do is we'll use re.search to search. So again, we're going to look for the first repeat, just like we did before. And in this time, instead of calling re.search, we call this object that we created beforehand and we use the search function with it. And we just then pass it the query. You can see that if we were going to search a lot of different genomes with this same pattern, that this would be slightly more readable, and it would also be faster. So again, if we want to then look for print the match, you would say first repeat group of 1. So we run that. I have an error.
Genome, yes.
Ah, yeah, it should be genome sequence. Thank you. There we go. So again, we compile the pattern ahead of time with re compile. We just give it the pattern, and then we get an object back from this, which then we can apply the search function to. And when we do that, we don't give it the pattern because it already knows about the pattern. We just give it the query sequence. Okay. So we're doing something that's a little bit trivial at this point. We're finding a sequence we already know exists. So maybe we want to now try and find the spacer sequence. Let's find the sequence that exists between 2 CRISPR repeats. Okay, we don't know what it is. So let's take a look for that. So how might we do that? So I'm just going to scroll up here. And so let's find the got my example. Yes, find the spacer. I'm going to give a simple example first, and then we'll move in and use the spacer, just again for readability and for learning. So we're going to find the NC spacer. I'm actually going to type out the whole name, so because we have multiple ones. 0, 1, 1. Let's see. 0, 1, 1. So let's compile the spacer pattern. So this is going to be re.compile, like we did before. And we're going to use, very similar than that we did before, the let me start here. We're going to use the CRISPR repeat. And then we're going to add to that string something we want to search for. So this is going to be our capture group that because we're not capturing the repeat this time. So something we want, something unknown. And then we're going to add the CRISPR repeat again. So this should be flanked by the CRISPR repeats. So CRISPR repeats. So this isn't going to match anything because we have this something unknown here. So we have to use some sort of regular expression in here to grab this something unknown. So our regular expression could be any character multiple times. That probably would work. But maybe we want to be a little bit more explicit because we don't want this to work if someone gives us a protein sequence that just happened to be in the middle of that. You know, someone gave us some garbage data. We don't want that to work. So let's be a little bit more explicit, and we'll say that we want A, T, C, or G, and we'll have that 1 or more times. So this is our, I think we're missing a round bracket here. So hopefully I've got all the bits. So I'm going to try and run this, and that's good. I don't get an error message. Again, if this is a little bit hard to read, the same code is in the notes. So after we've compiled the pattern, I'll just add a comment here. This is compiling. Then we're going to search for the pattern. And to do that, we're going to make a new thing. So we'll call a new variable, sorry. So we'll call first spacer is going to be equal to this compiled object we just created. And we apply the search function to it. And we're going to search the genome sequence for it. And then we can print the spacer. So we can print first spacer dot group 1. So I'm missing another bracket, and I'm missing something else here. No such group, probably because it's not finding the group. So let's go back and let's check out the type first. So let's go type of first spacer. We've got a match object. That should be fine. Print first spacer dot. No such group. Where is my typo? Let me just copy this. Nope. Should have a group 0. It's not capturing my group for some reason. Give me a second. Aha, this is why. My quotes here are outside of my capture group. That's my error. Okay, so I was doing string concatenation, but I wasn't including, by having my brackets outside of my quotes, I wasn't including them. And that's your capture group. So this is what we want to capture. So let's go back and look at, and then I'll explain how I got something with group 0. So group 1, this is the spacer sequence here. So this is an unknown sequence that we were looking for. So let's take a little, let's decompose this pattern that I kind of fumbled with here. So the first part of the pattern is going to be the CRISPR repeat. And what we're adding to that with our regular expression is this, which is a regular expression, means it can be A, T, C, or G, and then the plus sign on the outside means 1 or more times. And then when we look at this pattern that this regular expression that we're feeding in, because it has these round brackets, this tells Python, the RA search function, that this is the capture group I'm interested in. So you're going to match the whole thing, but the group 1 that you're going to return is going to be just this part of the match. I don't want the whole thing returned. Group 1 is going to match what's in the first set of round brackets. If we had a second set of round brackets, we would have a group 2, and that would match what's in the second set of round brackets. I also showed you here group 0, so let's take a look at what group 0 is again. So if I print first spacer dot group 0, we get a much longer string. And if we take a look at it, it begins with the same thing as the CRISPR repeat, which is the first part of our pattern match. So group 0 is actually what you searched for. Or maybe not what you search for, the entire match. And then group 1 through N is like different capture groups that you did. We only had one set of round brackets, so that's one capture group. But if we put a second set of round brackets, which we can do, so let's, for example, capture the second CRISPR repeat. So I'll add a round bracket here that we add on, and we have to add it on to the end. If we now run this, I'll just hang out here so you can see that code. So all we've done is added a second set of capture brackets around another part of the pattern. I can even throw this line of code in the Etherpad just in case someone's behind. Put it at the very end. So that's in the Etherpad now. So if we add those brackets, we still get the same first capture group. We still get the same group 0, but now we have a second capture group, or we should have a second capture group. So first spacer group 2 now gives us the CRISPR repeat. So we get as many groups for as many pairs of round brackets that we have, and we index them in the order that they occur. Okay. So the next thing that we're going to move on to, so I'm just going to check in with Davis in Ontario. Everything is going well there. Let me know in the Etherpad chat. Okay, awesome. The next thing that we're going to do is we're going to use a new function in Python called re.findall to find multiple matches. So like I said, re.search only gives us the first instance for that match. So we might need to find multiple things. And I'm actually going to have to pause.
So we're going to take a 5-minute pause as well. Tiffany takes a break and come back 5 minutes.
So does there have to be, I just copy it. Okay, so these ones, brackets start. So just CRISPR. CG, so plus over. Yeah, there you go. That should be.
Okay, Davis in Ontario. I'm back. Apologies, I'm getting over a really bad cold, and talking for this long is a bit tough on my vocal cords.
Not very much.
Okay. So, the next thing, hopefully I can continue. I'm feeling optimistic. So the next thing we wanted to do was look for multiple matches. So we're going to use the re.findall command for that. So let's just say here what we're doing. Okay. So the first thing we're going to do is compile the pattern again. And this time we know that there's multiple CRISPR repeats. So let's find those using re.findall. That's a simple thing for us to play with. So we'll look for the repeats. And we're going to say re.compile. And they're what we're capturing. So they're going to be in our capture groups. Okay, so that's our pattern. And then instead of using, very similar, instead of using the, we're going to use the compiled object, but instead of using the .search, we're going to use .findall instead. So we'll say all repeats going to be equal to repeats .findall.
I have a question. Are there advantages to recompile other than speed?
Just maybe for readability, because now you have this, if you're going to use this, so maybe I'll repeat the question. So the question is there, other than speed, is there advantages to compiling all the time? And so maybe readability. So if you're going to use the same pattern over and over again, and it's a complex pattern, it's just nicer to give it a nice variable name and just refer to that compiled thing. I guess you could also call it pattern. So yeah, it's speed and or maybe readability. You don't have to. Okay, so we're gonna then we're gonna print all the matches. But you can see we get a very different output when we use findall than when we used re.search. So when we used re.search, we had multiple group items that we could ask for. We could ask for the span to look for the position of these. Findall is great. It gives you a list of all of the things that match your regular expression, but it doesn't give you the position information and other information that you might be able to get from re.search. So that's a big difference between the two of them. If we want to find the position of multiple matches, we need to use a different function. So we have to use a function called finditer. And what this gives you back is an object that you can loop over. And as you loop over it, you can access not only what it matched, but as well as the positional information and other information you might be interested in. So we'll go through an example of that, and then we're going to try, I'm going to give you guys a challenge question. Okay, so we've already compiled the pattern, so we're going to not do that again. So we're going to, how am I going to do this? So let's call this first repeat matches. And this will use the repeats that we just compiled above. And then instead of find all, we're going to apply finditer. Genome sequence is what we're going to search. And then, so this is, and then we are going to loop over the finditer object and print the start and end positions and the sequence. This time, so I'm just using the same compile pattern we did for find all. So we're just looking for the repeats. So just the multiple repeats. Good question. So we'll say for match in first repeat matches. So this is the object that we got returned from finditer. And we're going to print the start and the group. So when we run this, you can see that not only do we get the multiple matches of this sequence back, we also get the start positions. So it depends. You have to pick these functions that you're going to use in Python depending on what you're trying to do. So if you have you just want to find the first instance of something and you might be interested in the position and maybe a bit more information, which you can look up in the documentation, fine. You know, re.search is a very easy, straightforward thing to do. If you want to find multiple occurrences, then you have to think about, do I just want to identify them and I don't care where they are and I just want to pull those sequences out? Then find all is your friend. And if you want more information again, then you have to go a little bit more complicated using finditer to get an object that you're going to have to loop over to grab the information from. So any questions about these things before we move into the challenge question from SFU, Davis, or Ontario? No? Okay, great. So the challenge question is challenge question 6 here. I'm just going to minimize this. So remember that when we first loaded the repeats, we had a dictionary that had multiple repeats in it. So I want you to try and find and print the spacer for the second CRISPR repeat, and then find the positions for the repeats and the spacers. Okay? Let's just focus on the top two, the first two. We can talk. And I'll just mute us here. I'm just going to pipe in here that I made a little mistake, and CRISPR's 1 and 2 are the same. So let's try the challenge question with CRISPR 4. So I've updated the Etherpad for that. Okay, so I think that, yeah, so I made a couple boo-boos in the challenge question. So CRISPR 1 and 2 are the same. CRISPR-4, there's only one repeat, but CRISPR-5 does work. So I'm going to update the question to 5 for the next time that I teach this. And if anyone wanted to continue the exercise here, do we have some, I think we have a solution here at SFU, right? Yep, so if we can paste that into the Etherpad under question number 6, if you can paste in the solution for 5. And Davis has worked ahead and answered question 7, even though I haven't taught that yet, so that's really awesome, and they're super keen. Okay, so this is the solution for the challenge question, and I'm not going to go in it over great detail because it's essentially just redoing, a lot of it's redoing the same code that I just showed you with finditer to grab the repeats positions, but in addition to that, you put capture groups around the repeats. So then you're able to access. Or I guess we haven't got this in this solution. You have it in your solution, don't you? The two capture groups.
I did that.
Oh, we haven't done that yet. Okay, so why don't we actually do this together then? So I'll grab this code, and we'll go over it all together for the 5th one. So my indentation is going to be a bit off probably. Not too bad. Sometimes it doesn't copy well from the Etherpad. Okay, so what we are using CRISPR-5 instead of CRISPR-1. So the difference is that we have to change the number for the dictionary of what we're going to access. The other difference is we need to capture the repeat as well as the sequence. So we'll have multiple capture groups. So we need to add a capture group here. As well as here. And we'll have to do that probably for the 2nd one as well to keep it in context, which we've got here as well.
Need another plus.
Thank you. Right here, right?
Yep.
Great. So we have 3 capture groups. So we want to capture the repeat before, we want to capture the spacer, as well as the repeat afterwards, so that we can get the sequence and the position for all of them. So we're going to call this, I'm just going to call this repeat and spacer, so that it's a little bit different from the thing above. And we'll call this repeat and spacer matches. And then we are going to loop over this object. And the first time we loop over, we'll do it for group 1. We'll also add a line printing it for group 2 and group 3. We could maybe do a nested loop, but I'm not going to get into that. So hopefully this will give us what we're looking for. And there we go. So we have the repeats for 5, the position, as well as the spacer and the position for that. So I'll paste this working code into the Etherpad so that you guys have an example of how to do this. But really the trick wasn't that much more. It was just adding extra capture groups to the code that we'd already developed to just access the repeats. Okay, and I'm just going to erase this other one here. All right. So what we're going to move on to next is we've learned how to use regular expressions. We've learned how to use regular expressions in Python. Now the next thing we're going to learn how to do is how do we know that a regular expression we create is correct? And so we only have 15 minutes left, so I'm not going to have time to have final challenge questions. We'll just do this as a demo for you to show you how we can build up some tests so that we can make sure that we have an accurate regular expression. Now I'm just going to head over to the notes to kind of set the stage. So we're moving away from CRISPR. And the example that we're going to talk about now is finding a transcription factor binding site. So transcription factors recognize sequences of DNA, usually in the promoter regions of genes. And what they bind to isn't always an identical sequence. They have some amino acids that are absolutely necessary for their binding, and then there's some almost like wobble bases around there that they prefer to bind to, but they don't necessarily always have to. And probably how long and the strength of their binding differs based on how well the sequence matches to what the transcription factor prefers. So you can imagine, here's an example for a transcription factor from my favorite organism, the nematode C. elegans. This is the transcription factor binding site for ELF1. And it likes to bind to a site, a sequence that either starts with an A or a T. It strongly prefers C at the second region. Then you can have T, C, or A at the third position, G or T at the second position. Then it really strongly prefers G, T, T, and then you can have T, C, or G at the end. So you can imagine, or you can envision with the tools we've learned today, we can easily come up with a regular expression to look for this, right? But we want to make sure that it's correct. So let's go through this together. We're going to build a regular expression to match this transcription factor binding site. We're going to wrap this in a function, and then we're also going to build a test function to make sure that our function works correctly. Sound good? Okay. And Ontario and Davis, you still with us? Just check in on the Etherpad. Great. Got it. Good. Okay. So before we even start to, I'm going to add in a new cell here. Testing regular expressions. Okay, so before we even start to develop our regular expression, we're going to build our test function first. We're going to think about all of the, not all of, but a few of the edge cases that we might encounter and what we should expect out of a function that that would match that regular expression. Okay, so our function is going to take a sequence as an input, and it's going to return to us a matching sequence as an output if it matches. Does that make sense? Okay. So we're going to make a function called test. Oh, I'm frozen. All right. Still looks good on our end. Pardon? I'm not on Wi-Fi. I'm hardwired. Okay, well, we'll just hang out. Oh, you're back. Okay, great. I'm back. All right, so we're heading. Maybe I can just have you guys. Did you miss much, or what was the last thing you heard? Well, I'll just Okay. So I'll just briefly say that we're building first a test function for our regular expression function, and our regular expression function is going to take in a query sequence and give us back a match if it exists. So we're going to call this test ELF1, that's the name of the transcription factor, consensus. And we are going to build, we haven't yet built, we're going to build a function called ELF1 underscore consensus. And we're going to, inside this test function, we're going to have some assert statements that are going to let us know if the code does what we expect it to or not. So we'll start out with one case. So we are going to assert that ELF1 consensus, if given an empty string, we give it an empty string, it should give us back nothing. right? If we give it an empty string, or just query, we shouldn't get a match back. So that should be what our function does. Another thing that we don't want it to do is, what if we give it, again, a protein sequence? We shouldn't get a match back, right? That's what we don't expect a match. So let's write a test case for that. Okay. So let's take a look at, this is kind of going to be difficult with the window sharing, but we'll get there. The next one is that, what if we give a incorrect nucleotide for the first here? We don't want that to match, okay? So let's give it an example where it gets pretty much a string that's going to match, except for the first nucleotide doesn't match. So that should also give us none, because we don't expect a match. And then we'll give it an example of one that should match. Or we'll give it one more that it doesn't match, and then one that should match. So in this one, I'm going to take a peek. Which one did I design here? So this one, the second nucleotide is incorrect. So we'll make a sequence where the second nucleotide is a T, should be a C, so it's not going to return it. We don't want it to return a match. Just copy this, it's the same. And then the last thing is, let's give it a case where we give the correct sequence, and we want it to match that sequence. So it should return the same thing that we input it. To just give us back what we provided. And if that doesn't happen, we should get an error that should match this sequence. Okay. So
Your first assert is EFL, not EFL.
thank you. Probably would trip me up for a while. Okay, so let's run this test sequence. Or not run it. Let's load the test function into memory, and now let's try the test sequence. And we expect it to fail because we haven't made the function yet. But let's just see what it looks like when that happens. So we'll say test ELF1 consensus, and we do get an expected error, and we get an error because this is not defined. So let's define the function and start to build it. And let's build it just for the first test case, okay? So we'll make our function called ELF1 consensus. And we're going to give it a sequence to search. That will be the input. And the first case is if we get an empty sequence. So let's say if sequence to search is equal to the empty case, then we're going to return that. All right. So let's load this into memory, and let's try and run our test case again and see what happens. Now we expect that it's probably going to trip up on one of these other asserts that we've written. So let's go test, ELF1, consensus, and we do get an assertion error. And our assertion error is that it should match the sequence. So it points us exactly to what assert went wrong, and it's because when it feeds the function an expected sequence, it doesn't match it because we haven't written the regular expression yet. So let's go ahead and write the regular expression now and the return from the function and see if we get it correct. So then at this point, we're going to expect after we add this to the function that we won't hopefully not get any assertion errors because it's going to match sequences that we want it to match and ones that it doesn't. But if we screw up our regular expression, having this test function is really useful because it will let us know that we've made a mistake. And we don't find it like some months down the line when we're getting a weird list of data that we're talking to our supervisor about. Okay, so let's add on to this function. So let's do first ELF1 site is equal to RE dot, we're going to use the findall function. And we're going to build our regular expression. And again, I'm just giving a demo, so this is one I pre-baked ahead of time. And you can, if you want to open up the image on your of the preferred transcription binding site while I'm writing this out, that might be helpful. So we want it to be an A or a T for the first position. It has to be a C for the second position. It could be T, C, or A for the second one. Then it has to be G, G, T, T. And then the last one can be T, C, or G. And then the sequence that we're going to search is what we input into the function, so sequence to search. So now we have to deal with the return. So we're only going to return something if there's something to return. So we'll say if first ELF1 site and we'll return that. So if it's not none, we'll return the match. And then otherwise, we'll return none for any other case. So that's our function. So now we'll run our test sequence and see if it works. See if we came up with a good regular expression. And we ran our test sequence, and we don't get any assertion errors. So we can be confident that at least the edge cases we thought of ahead of time, it works. Now there's one edge case I actually didn't think about ahead of time. So what happens if you get a, if you feed in, well, let's take a look at my regular expression. It's all capital letters. What happens if we get a sequence in lowercase letters? That's totally valid. So let's add that example to the test case. I didn't think of this, so I'm going to add it now. So if I get the same sequence as above, it should match for lowercase letters. So it should match this sequence. So what happens now when I run my test is I get an assertion error. And I get an assertion error because it's not working with the lowercase one. So we learned some strategies in our regular expression, so we could actually change our regular expression. But there's another little trick that you could use when you're in Python that is more Pythonic and less regular expression-y. We can, if we compile the pattern ahead of time, then we can use an additional argument that tells it to ignore the case. And so then we can use it for both uppercase and lowercase. So let's modify our function so that happens. So let's compile a function to do, or make a compile object, called EFL1 pattern using re.compile. We're going to move our pattern from here up to the compile. And we're going to add re.ignore case. And everything else should stay the same. And this should solve our problem. So if I run the function, or if I add the function to memory and now run our test case, it's still not working. What did I do here? Type error. Missing, find all is missing a positional, okay, that's my error. Because I'm using compile, I don't use re.findall, I use elf1 pattern.findall, right? Now if I add this function back to memory and run my test case, my test function, I don't have any errors, and now I have a regular expression function that will take in a sequence, and it will give me back a match if it matches, and I'm confident that my regular expression is what I want it to do, because this function that I wrote passed all of these test cases that I thought about ahead of time, mostly ahead of time. Does that make sense, and does that seem like a good thing to do, to write these test cases? Yeah? Great. So that's rounding out the top, or we're at 12:14. We're supposed to end at 12:15, so I can take a minute or two if anyone has any questions from SFU, Davis, or Ontario. Otherwise, then we're going to call it the end of the workshop. And I'll paste that code in the Etherpad. Well, it's in the notes, so you guys should have that in the notes. No questions from Davis. Great. No questions at SFU. Oh, we have one question at SFU. Yeah.
Back to the challenge question 6.
Yep.
Why did all of the, each of those match groups have the same coordinates?
Why did each of the match groups have the same coordinates? Back here.
Yeah.
That's a good question.
Because the span is just for the whole match.
The span is for, thank you.
Okay.
The span is for the match.
So even though individual elements
Yeah.
have all different places in that?
That's a good point. Okay, so yeah, that's something I didn't notice. So if you wanted, I think if you wanted to do that, maybe you would do three different compiles,
Okay.
or three different patterns with 3 different capture groups. Yeah,
Because
think so.
The groups don't store the positions either.
it's just the spans. Okay,
Yeah.
great.
One thing that's kind of weird about that, though, is
Yeah.
with that code, if I put in sequence 1 versus sequence 5, I think I'm getting the same result on the indices.
Okay,
So I'm wondering if something going wrong.
okay. We'll take that up. We'll take a look at that in a sec. But I think we'll sign off from now. The other workshops, so with the other ends. So we're going to say goodbye from SFU. Thanks for participating. Again, the notes are online if you want to look at things later. And have a good afternoon.
Thank
Okay.
you so much.
Thank you, guys.